And welcome to our today's lecture on the constituents of matter. In this lecture, we will understand the constituents of matter, structure of atom, the energy level of electrons, the formation and function of molecules depend on chemical bonding between atoms. The objectives of our today's lecture are: number 1, to give a general idea about the matter; number 2, to give a precise account of constituents of matter; number 3, to give a general and thorough account of structure of atom; number 4, explaining in brief the concept of energy level of electrons; and number 5, explaining the formation and functions of molecules. Now, let's start with the matter. Matter is everything around you. Atoms and molecules are all composed of matter. Matter is anything that has mass and takes up space. Matter is sometimes related to light and electromagnetic radiation. Even though matter can be found all over the universe, you will only find it in a few forms on Earth. Matter commonly exists in 4 states or phases, that's solid, liquid, gas, and plasma. However, advances in experimental techniques have revealed other previously theoretical phases, such as Bose-Einstein condensates and fermionic condensates. Before the 20th century, the term matter included ordinary matter composed of atoms and excluded other energy phenomena such as light or sound. This concept of matter may be generalized from atoms to include any objects having mass even when at rest, but this is ill-defined because an object's mass can arise from its possibly massless constituents, motion and interaction energies. Thus, matter does not have a universal definition, nor is it a fundamental concept. Matter is also used loosely as a general term for the substance that makes up all observable physical objects. Matter should not be confused with mass, as the two are not quite the same. For example, mass is a conserved quantity, which means that its value is unchanging through time within closed systems. However, matter is not conserved in such systems, although this is not obvious in ordinary conditions on Earth, where matter is approximately conserved. Coming to the constituents of matter. Molecules are built up from the atom, which is the basic unit of any chemical element. The atom in turn is made from the proton, neutron, and electron. It turns out that protons and neutrons are made of varieties of a still smaller particle called the quark. At this time, it appears that the 2 basic constituents of matter are the lepton, of which the electron is one type, and quark. There are believed to be 6 types of each. Each type of lepton and quark also has a corresponding antiparticle, a particle that has the same mass but opposite electrical charge and magnetic moment. An isolated quark has never been found. Quarks appear to almost always be found in pairs or triplets with other quarks and antiquarks. 2 theoretically predicted 5 quark particles called pentaquarks have been produced in the laboratory. 4 and 6 quark particles are also predicted but have not been found. The most familiar lepton is the electron. The other 5 leptons are the muon, the tau particle, and the 3 types of neutrino associated with each: the electron neutrino, the muon neutrino, and the tau neutrino. The 6 quarks have been whimsically named up: down, charm, strange, top or truth, and bottom or beauty. The quarks found in ordinary matter are the up and down quarks, from which protons and neutrons are made. A proton, for instance, consists of 2 up quarks and a down quark, and a neutron consists of 2 down quarks and an up quark. The pentaquark consists of 2 up quarks, 2 down quarks, and the strange antiquark. The notion that the world consists of particles goes back to the ancient Greeks, who proposed that the world consists of atoms. Here is a list of taxonomy of elementary particles ranging from molecules down to what are currently considered to be the most fundamental constituents of matter. Number 1, molecules. They are fundamental entities of chemically combined matter that possess the essential characteristics of large-scale matter. Number 2, atoms. Molecules in turn consists of atoms, which are the building blocks of molecules. Number 3, electrons, protons and neutrons. Atoms in turn consists of a nucleus containing protons and neutrons encircled by a cloud of electrons. Number 4, fermions and bosons. Protons and neutrons in turn consists of fermions, which are the basic constituents of matter. Bosons are the elementary force-carrying particles. Number 5, quarks, leptons and bosons. Fermions are categorized into quarks and leptons. Bosons are categorized into the gauge bosons and are also the recently discovered Higgs boson. The gauge bosons mediate forces. For example, the photon mediates the electromagnetic force, while the Higgs boson is thought to be responsible for particles exhibiting mass. Now let's discuss the structure of atom. The idea that matter is made up of discrete units is a very old one, appearing in many ancient cultures such as Greece and India. The word atom, in fact, was coined by ancient Greek philosophers. In the early 1800s, John Dalton used the concept of atoms to explain why elements always react in ratios of small whole numbers, the law of multiple proportions. Dalton also believed atomic theory could explain why water absorbs different gases in different proportions. For example, he found that water absorbs carbon dioxide far better than it absorbs nitrogen. Dalton hypothesized this was due to the differences in mass and complexity of the gases' respective particles. Indeed, carbon dioxide molecules are heavier and larger than nitrogen molecules. In 1827, botanist Robert Brown used a microscope to look at dust grains floating in water and discovered that they moved about erratically, a phenomenon that became known as Brownian motion. This was thought to be caused by water molecules knocking the grains about. In 1905, Albert Einstein produced the first mathematical analysis of the motion. French physicist Jean Perrin used Einstein's work to experimentally determine the mass and dimensions of atoms, thereby conclusively verifying Dalton's atomic theory. Coming to the definition of atoms. Atoms are the basic units of matter and the defining structure of elements. Atoms are made up of 3 particles, protons, neutrons, and electrons. An atom is like a tiny solar system. In the center of the atom is the nucleus, which is a cluster of protons and neutrons. The protons have a positive electric charge, while the neutrons are electrically neutral. The nucleus makes up almost all of an atom's mass or weight. Whirling at fantastic speeds around the nucleus are smaller and lighter particles called electrons, which have a negative electric charge. An atom has the same number of electrons, negative charge, and protons, positive charge, to make the atom electrically neutral. An extremely powerful force called the nuclear force holds the protons together in the nucleus, as they naturally repelled one another electrically. Protons and neutrons have approximately the same mass. However, one proton weighs more than 1800 electrons. Atoms always have an equal number of protons and electrons, and the number of protons and neutrons is usually the same as well. Adding a proton to an atom makes a new element, while adding a neutron makes an isotope or heavier version of that atom. Let's understand what nucleus is. The nucleus was discovered in 1911, but its parts were not identified until 1932. Virtually all the mass of the atom resides in the nucleus. The nucleus is held together by the strong force, one of the 4 basic forces in nature. This force between the protons and neutrons overcomes the repulsive electrical force that would, according to the rules of electricity, push the protons apart otherwise. What are protons? Protons are positively charged particles found within atomic nuclei. They were discovered by Ernest Rutherford in experiments conducted between 1911 and 1919. The number of protons in an atom defines what element it is. The number of protons in an atom is referred to as the atomic number of that element. The number of protons in an atom also determine the chemical behavior of the element. Electrons. Electrons have a negative charge and are electrically attracted to the positively charged protons. Electrons surround the atomic nucleus in pathways called orbitals. The inner orbitals surrounding the atom are spherical, but the outer orbitals are much more complicated. An atom's electronic configuration is the orbital description of the locations of the electrons in an unexcited atom. Neutrons. Neutrons are uncharged particles found within atomic nuclei. A neutron's mass is slightly larger than that of a proton. Like protons, neutrons are also made of quarks, one up quark and two down quarks. Neutrons were discovered by James Chadwick in 1932. What are isotopes? The number of neutrons in a nucleus determines the isotope of that element. For example, hydrogen has three known isotopes: protium, deuterium, and tritium. Protium, symbolized as 1H, is just ordinary hydrogen. It has one proton and one electron and no neutrons. Deuterium, D or 2H, has one proton, one electron, and one neutron. Tritium, represented as T or 3H, has one proton, one electron, and two neutrons. Chemical reactions involve either the transfer or the sharing of electrons between atoms. Therefore, the chemical properties of an element are primarily dependent upon the number of electrons in an atom of that element. Protons also play a significant role because the tendency for an atom to either lose, gain, or share electrons is dependent upon the charge of the nucleus. Therefore, we can say that the chemical reactivity of an atom is dependent upon the number of electrons and protons and independent of the number of neutrons. Now let's discuss the energy level of electrons. Electrons are one of the three subatomic particles. They have a negative charge and about 1/1800 the mass of a proton. They are attracted to the positively charged protons in the atomic center, but they are repelled by one another. It is impossible to absolutely define the position, which is momentum and location, of an electron in space and time. Instead, electrons are described as having different probabilities of distribution around the atomic center. These volumes of space, where an electron is found more often, are called atomic orbitals. At the beginning of this century, it was already known that atoms were made of protons at the center, the nucleus, and electrons orbiting around them. Scientists later realized that the light emitted from a particular type of atom occurred at specific frequencies. That is, the light given off by a collection of atoms in the gas phase could only be of certain colors. To explain this observation, Niels Bohr proposed that electrons inside an atom occupy only certain allowed orbitals with a specific energy. In other words, the energy of an electron in an atom is not continuous but quantized. The energies corresponding to each of the allowed orbitals are called energy levels. If an atom, ion, or molecule is at the lowest possible energy level, it and its electrons are said to be in the ground state. If it is at a higher energy level, it is said to be excited, or any electrons that have higher energy than the ground state are excited. If more than one quantum mechanical state is at the same energy, the energy levels are degenerate. They are then called degenerate energy levels. To understand this better, think about a bookshelf. Each shelf contains books just like how each possible orbital in an atom contains electrons. Each shelf is different to the others, just like how each orbital represents different energy levels for electrons. An electron can't have an energy value halfway between two energy levels in an atom. Similarly, a book cannot be placed halfway between the consecutive shelves. It can only be placed within one shelf. Each energy level is labeled with the quantum number n, where n can be 1, 2, 3, 4, and so on. And the energy of a particular level can be determined by En is equal to minus 2 pi square mz square E4 divided by n square h square. Quantized energy levels result from the relation between a particle's energy and its wavelength. For a confined particle, such as an electron in an atom, the wave function has the form of standing waves. Only stationary states with energies corresponding to integral numbers of wavelengths can exist. For other states, the waves interfere destructively, resulting in zero probability density. The first evidence of quantization in atoms was the observation of spectral lines in light from the sun in the early 1800s by Joseph von Fraunhofer and William Hyde Wollaston. The notion of energy levels was proposed in 1913 by Danish physicist Niels Bohr in the Bohr theory of the atom. The modern quantum mechanical theory, giving an explanation of these energy levels in terms of the Schrödinger equation, was advanced by Erwin Schrödinger and Werner Heisenberg in 1926. Now let's try to understand the formation and function of molecules. Covalent bond is the sharing of a pair of valence electrons by two atoms. Two or more atoms held together by covalent bonds constitute a molecule. A single bond is a pair of shared electrons. This notation, which represents both atoms and bonding, is called a structural formula. For many molecules, the sharing of electrons allows each atom to attain the equivalent of a full outer shell, corresponding to a stable electronic configuration. Covalent bonding includes many kinds of interactions, including sigma bonding, pi bonding, metal-to-metal bonding, agostic interactions, bent bonds, and three-center two-electron bonds. The term covalent bond dates from 1939. The prefix co means jointly, associated in action, partnered to a lesser degree, etc. Thus, a covalent bond in essence means the atoms share valence. In the molecule H2, the hydrogen atoms share the two electrons via covalent bonding. Covalent bonding does not necessarily require that the two atoms be of the same elements, only that they be of comparable electronegativity. Covalent bonding that entails sharing of electrons over more than two atoms is said to be delocalized. A charged atom is called an ion, a positively charged atom is called a cation, while a negatively charged atom is called an anion. Cations and anions are attracted to each other. The attraction is called an ionic bond. Compounds formed by ionic bonds are called ionic compounds or salts. The term covalence in regard to bonding was first used in 1919 by Irving Langmuir in a Journal of the American Chemical Society article entitled The Arrangement of Electrons in Atoms and Molecules. Langmuir wrote that we shall denote by the term covalence the number of pairs of electrons that a given atom shares with its neighbors. Now that we have looked at the structure of atoms, we can move up the hierarchy of organization and see how atoms combine to form molecules and ionic compounds. Atoms with incomplete valence shells can interact with certain other atoms in such a way that each partner completes its valence shell. The atoms either share or transfer valence electrons. These interactions usually result in atoms staying close together, held by attractions called chemical bonds. The strongest kinds of chemical bonds are covalent and ionic bonds. Atoms of most of the elements do not exist independently. They either form molecules or ions. Molecules are formed by a combination of atoms or ions by chemically bonding to each other or held by attractive forces due to the charges. A molecule is the smallest particle of an element or compound which is capable of independent existence. If the molecule is made up of atoms of the same element, it is said to be homoatomic. For example, oxygen and nitrogen. If the molecule is made up of atoms of the different elements, it is said to be heteroatomic. Examples: carbon dioxide, water, sulfur trioxide, and hydrochloric acid. According to the octet rule, elements are most stable when their outermost shell is filled with electrons. This is because it is energetically favorable for atoms to be in that configuration. However, since not all elements have enough electrons to fill their outermost shells, atoms form chemical bonds with other atoms which help them obtain the electrons they need to attain a stable electron configuration. When two or more atoms chemically bond with each other, the resultant chemical structure is a molecule. The familiar water molecule consists of two hydrogen atoms and one oxygen atom which bond together to form water. Atoms can form molecules by donating, accepting, or sharing electrons to fill their outer shells. Now let's have a look at a variety of molecules. Molecules can be simple or complex. They can even be made up of just one atom. The element argon is one atom molecule. Other molecules can consist of two atoms of the same element. The oxygen molecule is made up of two oxygen atoms bonded together. However, in certain circumstances, three oxygen atoms bond together, forming a molecule called ozone. All around you, molecules are changing and rearranging their atoms in chemical reactions to form new molecules and new compounds. When you breathe in oxygen, it goes through a chemical change inside your body and forms a new compound, carbon dioxide, which you breathe out. Catalysts are special types of molecules that speed up chemical reactions but do not actually change themselves. They are used, for example, in catalytic converters in cars. Now, at last, let's try to learn about bonding. When atoms join together to form molecules, they are held together by chemical bonds. These bonds form as a result of the sharing of exchange of electrons between the atoms. It is only the electrons in the outermost shell that ever get involved in bonding. Different atoms use these electrons to form one of three different types of bonds: ionic bonds, covalent bonds, or metallic bonds. Ionic bonds. In ionic bonds, electrons are transferred from one atom to another. When sodium and chlorine combine to form sodium chloride, sodium loses an electron and becomes positively charged. Chlorine takes that electron and becomes negatively charged. Ionic bonds are difficult to break. Ionic compounds are usually solids with high melting points. Covalent bonds. In a covalent bond, electrons are shared between two atoms. When two oxygen atoms bond together to form an oxygen molecule, they share 4 electrons, 2 from each oxygen atom. Other examples of covalent bonding are water, H2O, and carbon dioxide, CO2. Covalent compounds are usually liquids or gases with low melting points. Metallic bonds. Metal atoms are bonded to each other through metallic bonding. In this type of bonding, all the atoms lose electrons, which float around in a common pool. The electrons in this pool can move around freely, which is why metals can transfer heat or electricity so well. If one part of the metal is heated, the electrons carry the heat quickly to other parts. That's the end of our today's lecture. Hope it was helpful for you. Thank you for watching and